So to diagonalize this matrix, first we're going to need to compute the eigenvalues. Okay, so then I find the characteristic polynomial first. So the characteristic polynomial, since this is 2 by 2, so I can use this shortcut times lambda plus the determinant of A. And the determinant of A is 9 times negative 6 minus 4 times negative 14. This is negative 54. So the determinant of matrix is 2. And the trace of this matrix is the sum of diagonal entries. So it's sum of these numbers, which is going to be positive 3. So then the polynomial is lambda squared minus 3 lambda plus 2. And we call this characteristic polynomial of A. And then you set this to 0 to find eigenvalues. So this will be lambda minus 2, lambda minus 1 equals 0. Lambda equal 2, this is lambda 1, I'm going to call it lambda 1, lambda 2 equals 1. And since these are distinct, so we have distinct eigenvalues. So there is a theorem that says if your eigenvalues are distinct, then the matrix is diagonalizable. So of course, now we can find the eigenvectors corresponding eigenvectors to build the matrix P and write the factorization. Okay, so now let's find the eigenvector corresponding to lambda 1. So I'm going to say, so find eigenspace corresponding to lambda 1, okay, which is going to be this. So I'm going to look at A minus lambda 1 times identity, which is A minus 2 identity. And then this means you're going to subtract 2 from the diagonal entries of A. And the diagonal entries of A are 9 and negative 6. I'm going to subtract 2 from those. So subtract 2 from 9, 7. Then subtract 2 from 6, that's negative 8. Okay. Then now we can just divide the first row by 7, and this will be 1, negative 2. And then you can also divide this one by 4, so this will be 1, negative 2. And you see the second row and first row is the same thing. So if you reduce it, then this will completely be 0. So now we have this. So we're going to have V1, so I'll just call X1. So X1 minus 2X2 equals 0, and X2 is a free variable. And this will lead to X1 is 2X2, and this is X2, so X2 will be 2, 1. So this is my first eigenvector. So basically the eigenspace looks like this. Eigenspace is the span of a single vector, which is 2, 1. Dimension 1. And then similarly, I'm going to compute eigenspace corresponding to lambda 2, which lambda 2 is 1. So this is going to be A minus identity. And I'm going to subtract 1 from the diagonals. So this will be 8, negative 14. Or subtract 1, that's negative 7. And then you can, and then we can now do, so let's say if I divide the first row by 2, then I'll get 2, negative 7, and then this will be 4, negative 7. Let's see, so I subtract 1. Okay, that's 8. Yeah, negative 14, yes. So now I can just multiply the first one by 1 and by negative 2 and add it to the second one. So we need to have a free variable here, but are we getting a free variable? So there is, let me see, there is something. So I subtract 1 from the diagonal entries, right? My second eigenvalue is 1. So therefore, subtract 1 from the diagonal, so that's 8. And this is negative 7, this is 4, 14. That's what I'm seeing actually. Okay, so if I take the, okay, so the first one is, oh, this is 4, sorry, this is when I divide, yeah, this is 4. Now the first and the second row are the same, so this will be completely 0. This is 4, negative 7. And then when you rewrite this, this is going to be 4x1 minus 7x2 equal to 0. And x1 equals 7 over 4x2, and x2 is free. So now the second eigenvector is going to be 7 over 4x2 times x2, and you can write this as x2 7 over 4 and 1, you can multiply this by 2. It can be written like this too. So 7 and 4. It can also be written like this. So then eigenspace corresponding to lambda 2 is the span of this vector. Okay, this is going to be eigenvector basically. So then the matrix P is going to be, this is going to be the second eigenvector. And the first eigenvector was 2, 1. 2, 1, it's this. And then the matrix D is a diagonal matrix that has lambdas on the main diagonal and zeros here. And the P inverse, we can just compute it by 1 over determinant of P. And then we just swap these two entries for 2 and then change the sign, -7, -1. And the determinant of P is 8 minus 7, that's equal to 1. So P inverse equals 4, -7, -1, 2. That's P inverse. Okay. And that's basically what this diagonalization for A is basically.